in this part, I will talk about the Schottky barrier. So as you know, whenever you have a metal and a semiconductor interface, whether the semiconductor is 2D or 3D, we always have a Schottky barrier. Schottky barrier, by definition, is the potential energy which the electron needs to overcome in order to pass from one side to another side. There are two mechanisms for the electron to pass. The first one is the thermoionic emission, which means that the electron will need a sufficient thermal energy in order to pass from the metal to the semiconductor. The second mechanism is the field emission, which means that the electron will tunnel from the metal to the semiconductor if the depletion layer is narrow enough. One solution for the 3D materials to overcome the Schottky barrier is to use doping. However, for 2D materials, we cannot use doping since you will destroy the crystal lattice and you will introduce defects. So the only solution which you need to use is to find the 2D material which make a very small Schottky barrier with the metal. With that being said, the Schottky barrier is not the only problem. We need to take into account the interfacial interaction. So whenever you have a metal on top of a 2D material, the interfacial interaction can differ. And in fact, you have three scenarios. The first scenario is that you have a very weak adhesion between the metal and the 2D material. They are attracted only by van der Waals force. So instead of having only the Schottky barrier here, you have an additional barrier due to van der Waals force. So as you see, the thermoionic emission is not probable, and at the same time, since the depletion layer is very wide, also the field emission is not probable. The second scenario is that you have a partial overlap between the metal and the 2D materials with surface states. These surface states are traps for the electrons, and in the same time, if they are full, they can reduce the kinetic energy of the electrons by scattering. And the third scenario, which is the perfect one, where you have a strong hybridization between the metal and the 2D material, and the only problem that you need to take into account is the Schottky barrier. So in the end, to conclude, when having a 2D material in interface with the metal, you need to choose the material in such a way that they make a very small Schottky barrier, and in the same time you need to choose materials which make a very strong hybridization, they need to make a full covalent bonding. And that's it. Thank you.